So far we have learned about the curve fitting of the fitting a straight line and also curve fitting for the general linear least square. So now we want to, in this lecture, we want to learn about the polynomial interpolation. Curve fitting, but the polynomial interpolation. So in this lecture, we are gonna work on the, we are gonna have one or two slides of the introduction, then the system condition. We learn about the system condition, the Newton interpolating polynomial, the linear interpolation, quadratic interpolation, and general form that we would have. At the end, we are gonna talk about the Lagrange interpolating polynomial. So we are talking about the polynomial, right? So it makes sense that we would have the polynomial equation here. So with this polynomial equation, we would say a1, a2x, and it can go to the x power n minus 1. So let's consider this one as like our equation. So we would say for n data point, there is one and only one polynomial, right, of order n minus 1 that can pass all of the data points that you have. Like, for example, I have 1 point here, 1 point here, 1 point here. If I say that, like, for example, I have 5 data points, in fact, you would have one and only one polynomial of order 4 to pass all of those data, like 5 data points that you would have. There is a simpler example here. For example, a straight line, we would say the polynomial of degree 1, right? So you have 2 points, let's say one here, and you want to connect it. So it's going to be one line with the polynomial of degree 1, right? So we'll pass through 2 points. Polynomial interpolation consists in determining the unique n minus 1th order polynomial that fits the n data points. So we are going to talk about it a little more. If we recall, like we call the MATLAB, we consider the coefficient of the polynomial in somewhat different manner than we usually do. For example, instead of using the increasing power of x, in MATLAB, we would say that let's have it like in the decreasing power. So let's have it like that, because after all of these ones, our hope is that we can develop all of these codes in MATLAB or any other languages. So we want to make a code for it. So this is the our function. This is the same things that we had in the previous page, like on slide number 4. The only thing happen is that I have like p1 x power n minus 1, p2 x power n minus 2, and then it's just stay in the decreasing order. So a simple way to do the polynomial interpolation is like that. Would be that from knowing x and f of x to solve a system of n equation with the n unknown p1, p2, pn. Let's have an example that in that case is going to make more sense. We want to find the polynomial formula that passes through these 3 data points. So I have x1, f of x1 is this value, f2, f of x2 is this value, and the x3, f of x3 is going to be this. So when you look at it, you can make a guess quickly that you would need to have the polynomial degree 2, because you have 3 data points. So the best polynomial that we can use for these 3 ones is going to be degree 2. So we are looking at the polynomial of degree 2, which is y equal to p1x2 plus p2x plus p3. And these are the same things as a0, a1, a2 that we had before, but we just write down the polynomial coefficients that we have here, right? So because of that, we said that let's have it p instead of a, but it's the same. So we can find the following system of 3 equations. We just put the value of it. So it's like that. I had x1 and then y1, x2, y2, and x3, y3. So I put the value of it. I have 3 equations and I have 3 variables. So degree of freedom is 0. I can solve the question. In matrix form, and when we want to write it down, look at here is the 300, 400, and 500, right? These ones. and then this, which is the power 2, like the 300 power 2, 400 power 2, and the like a square of all of these ones, because here is like 302. So we just write down, got this matrix and wrote it down here. The last one, it doesn't have anything. It's like the similar as the anole that we had before. So the coefficient for this one is going to be 1. So we're going to put 1 here. And then we say this one times P1, P2, P3. It should give me this y. Right? This is the y that I wrote down as matrix here. So we want to solve this one. It's just the 3 equations with the 3 variables. We can solve it with the matrix form in MATLAB. And in MATLAB, we can use polyfit, for example, or we can use the like in the mathematic form and do the calculation, everything, the same things that we have learned on the concepts that we had before the midterm. So we can find it. So the preceding method is simple, but it has some serious problem. So when you look at this, we said that this one is we just use this one as the general form, right? So this type of the matrix, we call it van der Monde matrices. And these van der Monde matrices, they're very sensitive to the round-off error, right? When they are very sensitive to the round-off error, we call them, they are very ill-conditioned. So that's the problem that we have for this. Look at here, for example, I have these 2 equations. There's no solution for it, right? I have these 2 that they're singular, so they have infinite solution. And look at this one. They are not parallel, or they are not like singular. It's not like that. They are just overlapping each other. Here we have some points, but this is when you say ill condition is like this. You don't know which point is going to be the answer. It's going to be here, it's going to be here. Maybe your eyes would say here. So with this one, we would say it's an ill condition system. So when we have the ill condition, so that when you want to get the answer, it's not easy to find it. So let's talk about the system condition a little. So this applies to a system of the form, let's say we have A times X is B. It's exactly the same equation that we had before. There are several types of the norms, but those of more interest to us are the Euclidean and Frobenius forms. So we are going to try to use another approach. In the Euclidean form, what we are going to do is that we are going to define the norm for the x, and we would say, okay, so the Euclidean norm of this x is going to be like a square root of the xi power 2. And then for the Frobenius form, what we are going to do is that we would say, okay, so this is the Frobenius. We are going to say it's the sigma of the A of the ij, like A that we would have here. And the Frobenius one, when you look at it, it's I equal to 1 to n and j equal 1 to n. So it means that this is the norm to the square matrix, right? So these are 2 different norms that we have. When we are talking about the matrix condition number, when we want to find it, what I would say? We would say the condition number of the matrix A, because we want to see if it's ill condition or not, right? So we would say it's the norm of it, norm of A, times norm of A minus 1. So we are gonna, and we know the equation for the norms, right? We have it here. And then we can show it even like this. You can say delta x over x is equal to the condition of A of delta A over A, like norm of the delta A over A. And then we can say that this is a relative error of the norm of the computed solution. It can be as large as the relative error of the norm of the coefficient. So this is the delta x, right? So with the relative error, what did we say? We said that xi plus 1, for example, minus xi divided by the xi plus 1. So that's very similar to the relative error that we had before. So here it says that we can find out, it's very interesting, if we find out the relative error of the norms, we multiply it by condition, we are going to find out the relative error of the x, right? Even without finding out the value for the x. So we can find out the relative error of that one. So the MATLAB command for determining the condition number of matrix A is like simply you would say condition A. But if you want to do that by hand, you would need to use the equations on the previous slide, like slide number 9. So a condition number much greater than unity suggests that the system is ill-conditioned, right? For example, if my condition number is, look at this one, 5.893 times 10 power like 006, like, sorry, times e power 006. So this is the very high condition number. And then we said that when it's the condition number is huge, is great, so it's like our system is ill conditioned. So what does it mean when we find a condition number like this? Let's say we did we found the norm of the a and then we did all the calculation. So the condition number of the, like something like this, it means that about 6 digits of the solution would be questionable. So when you think about it, it's like that. Okay, so you get your answer 6 digits of those number that you have, because of the round of error that we had. So you can't trust it. So to solve the problem of ill-conditioned system, so what are we going to do? We are going to look at the two polynomial interpolation techniques. So these are the parts that we are going to use, the Newton polynomial interpolation technique and the Lagrange polynomial interpolation. So let's have a quick review from like before. When we say linear interpolation, this is the simplest form of interpolation, where 2 points are connected by the straight line. So they're linear, right? So when they're linear, it makes sense that you're going to connect them by a straight line. This is called the linear interpolation. In the next slide, we are going to see the graphical. So we're going to see the figure of it. So here we can easily find out like f1 of x minus f of the x1 over x minus x1 is equal to f of x2 minus f of x1 over x2 minus x1. So let me show you this. So then we can rearrange it and find out the value of the f1x. But we are going to go back to that one. So these are linear one, and I'm interested to find out this value. So what you can say, so okay, so whatever you have, like f of x1, right, minus f of x2 divided by x1 minus x2 is going to be equal to, you can say f of x1 minus f1 of x divided by x1 minus x, or you can say it's equal to the f of x1 minus f of x2 and then x minus x2. So it's the linear interpolation. And when we look at here, we call this one Newton linear interpolation formula. It's very similar to the Newton equation that we had before. So if we have if the distance between x2 and x1, it's small, it means that we have the smaller interval between the 2 points. So our approximation is going to be better, right? Because this is the real, so when you look at this x, the real f1 of x, you should go all the way up and it's here, right? So, and it happens here because our x1 and x2, they're really far away from each other. So probably we would need something a lot closer, like for example, x1 here and x2 here. In that case, we would find some answer which is closer to the real answer. So the 1 here in f1x, this entity of 1, it's like it shows that it's for the first order polynomial interpolation. So that was the first order, right? We can have the quadratic interpolation as well. In the quadratic one, I talked about that, right? So you saw that we had a huge error. So if f1 of x was here, but it should have been here. We didn't find it. Because of that is a huge error that we found. So we can introduce some curvature in the interpolation by using the second order polynomial, or we can name it as a quadratic polynomial. But in industrial application, we don't use this much, like this one, that much. So we're going to learn about the better one. But let's say this is the starting point for the curvature. So we need the three data points. We have the three data points. And then a convenient form for the quadratic equation is going to be like f second order of the like from the second order of the polynomial, it's going to be b1 plus b2 x minus x1 plus b3 x minus x1 and x minus x2, right? And then we have these things that, for example, we would say we want to determine of the b1, b2, and b3. So for b1, we would say we're just trying to solve that. We're going to set x equal to x1. So we're going to find that b1 is equal to f of x1. Let's go back to here. So if in this equation, I put down the x equal to x1, let's see what's going to happen. X equal to the x1. So this one is going to be x1. This one is going to be x1, right? So b2 is going to go away, b3 is going to go away. So we would say f2 of the x1 is equal to b1. So you can see here. So b1 is going to be equal to f value of the x1. You can write down 2 here as well to say that it's a second order polynomial. And then we are going to replace the b1 by its expression into the polynomial yield, and we are going to find out b2 equal to f of x2 minus f of x1 over x2 minus f. So we found that b2 as well. It's like that in this equation. We know what's the b1, right? b1 is f of x1, and then instead of x, we are going to put x2. So if you put instead of x, you put x2, what's going to happen? It's going to be f of x1 plus b2 x2 minus x1 plus b3 x2 minus x1 times x2 minus x2. So this one goes away. We can find out b2. So look at here. We would have b2 equal to f of x2 minus f of x1, x2 minus x1. And when you look at it, it's very similar, right? So we had something similar to this before. It's like a slope. And then we are going to replace it, replace the b1 and b2, and we would say x is equal to x3. And when you look at it, it's a similar approach. So we are going to find out b3. So we found that b1, the value of b1, b2, b3. And that's what we are looking for in our, like for the interpolating polynomial. We can have a general form of it. So that's the general form, which says that if n1, n minus 1, like the n minus 1 degree of the polynomial for the n data point, right, is going to be equal to the, if we say is equal to b1, b2, and then we're going to write down all of these like x minus x1 times x minus x2 until x minus x at n minus 1. That's a general form. For b1, we say that, okay, let's put x equal to x1, that this one is going to go away. For b2, we are going to find it out for the x2, right? And this b1, we are going to replace the b1. The same things for b3, we are going to find it for x3, and x2 and x1, we already substitute that before. And for bn, in fact, we are going to put it as the f of xn, and these are the things that we found it from the previous one. So, and here where the bracketed function are finite divided differences. So we can say, and we had, it's a Newton formula, the same Newton formula that we had before. So it's like f of xi and xj is like f of xi minus f of xj divided by xi minus xj, if you want to find it. And then you're going to find out xijk, so you're going to put it like this. And similarly for the nth one, when you want to find out the f of this bracket like this, you're going to use this equation. It's like that, you're going to put the f of xn minus 1 x2, so you're going to put it here. If you want to do that like by hand, you don't need to go through this one. You're going to find out B1, then B2, then B3, then B4, until whatever number that you have. The reason that I show you the general form of this polynomial, like the interpolating the polynomial, is that when you want to do coding, you need the general structure based on these symbols, right? So that's the main reason that I give you these equations here. So we can say these coefficients can use to yield the general form of the Newton interpolating polynomials. So it's like that f of the order n minus 1 at x is going to be equal to this. Like this equation is f of x1. This is the b1, right? Again, as I said, so this equation is the one that you can, it's a general form of it. But if you want to do that by hand, you can go with the example that we did in the previous slide. So we said that we can use the Newton and the Lagrange one, right? So Newton one, we learned it, but Lagrange one is very interesting. The Lagrange interpolating polynomial, let's start that we would assume that we write the interpolating polynomial as the weighted average. So this L1 and L2 is the weighted average. I would say my f of x, which is the polynomial, right? It's going to be polynomial function, is going to be weighted average times f of x1 plus some other weighted average times f of x2. And we call them like these coefficients of the L1 and L2 to show the weighted average. So we are going to call them weighting coefficients. So it makes sense that it's for the first weighting coefficient, we would say L1 is equal to x minus x2 divided by x1 minus x2. It's the same points that we had before, like in the previous slides. And likewise, we can say for L2, we have the x minus x1, x2 minus x1. So the second coefficient, which is this one, is the straight line equal to the 0 at x1 and to 1 at x2. So we're going to find out here. We're going to replace the L1 and L2 here. So we find out f1 of x, right? So it's like the first order. So like before, this f1 that we have here means that it's the first order polynomial. But I just put the weighted average. So this L's is the Lagrange weighting average. So the above equation is the linear Lagrange interpolating polynomial. So that's another method that we can use. So if we have the, let's say, to do so, we will need three weighted coefficients, which will represent three parabola passing through one point and equal to 0 at the other 2 points. So when we have like for the second order, so what's going to happen is like I have the first weighting coefficient, second one, and third one, because I'm talking about, I have 3 points. I'm talking about this like second order polynomial to fit on those 3 points. So these are the equations that we would have for the weighting, like weighted average of those ones. So we can generalize that. Instead of f of 2, we can write down like order 2, we can write down order of n minus 1. So what's going to happen, we would say the order of n minus 1, it's equal to the sigma, like we added all of these, right? Sigma of the Li, Lagrange of the Lagrange weighting average, at x, times f of xi. It can be f of x1, f of x2, f of x3. And then for these ones, we're going to use another equation, which is like pi, because these are like multiplication, right? Pi of the x minus xj and divided by xi minus xj. So when we have this, then we can go to the MATLAB and like or any other language like Python, and we can write down the general code for these ones. So we learned about the system condition, Newton interpolating polynomial and Lagrange interpolating polynomial. In fact, when the system condition, we have a ill-conditioned systems, it means that they're partially overlaps each other, like the lines. Then we can't go with those linear, like the methods that we had before. So we would go with the Newton interpolating polynomial, the Lagrange Newton polynomial. The next part of the curve fitting is the spline. So far we learned the general form of the least square, which was covering like all the multiple linear ones, simple polynomial one, and then we learned about the at the beginning and the simple one, and here we learned about the interpolating polynomial for the curve fitting to find out the um, like the point that is between the two points.